Okay, welcome back, everyone. So today we will revisit the question we started off with. So when we began thinking about random walks of animals, the primary context we thought about this was, when animals are looking for resources, they are trying to, find an optimum way to reach resources. And of course, if we also had an intuitive thought that if the resources were abundant and spread all over around, there was nothing much the animal had to do. They just had to move around and find food, right? Whereas if the resources were sparse, right, they should do because they don't know where the next resource patch will become available to them. So we thought, okay, maybe they have to move randomly. So we studied properties of, we defined a very, very simple random walk in one dimension, and we proved some properties of those random walks. And in the assignment, we have dwelled it further. And we now know both random walks in one dimension and random walks in two dimensions, right? So we have learned all those. Let us now dig further. Okay, so what did we learn so far? We have focused on the following quantities primarily, okay, which is, we thought of mean displacement, right? Mean displacement for 0 for unbiased random walk. Okay, so in the absence of any information, unbiased random walks makes the most sense. And the mean square displacement, we found that was proportional to time. Okay, and in fact, in the class itself, you proved that this result actually did not depend on the distribution at all. You found that the mean square displacement was equal to sigma square times t. Okay, where sigma square was the variance of the underlying distribution. So it did not really depend on any other properties of the distribution. In fact, I had asked you to prove for uniform distribution with the general value of the width of the uniform distribution. In fact, but in the derivation, you did not even use the fact that the derivation was meant for a uniform distribution. It shows that the result was very general. The fact that mean square displacement must be proportional to time seemed like a very, very general result. And in some sense, of course, we don't necessarily believe that very general result will be applicable directly as it is in an animal or biological context. But that one can think of these kind of simple mathematical formalisms as null models, right? This is our baseline expectation. And we can then think, how is it deviating? And if it is deviating, why is it deviating? So we can begin to ask those questions in a quantitative way. Okay, so in that context, the analysis of mean square displacement was very useful. Second, and then in the following class, we also looked at not just mean and variance, but also the entire density function. So because animals are moving and randomly so, their probability of being at any location will also change with time. We derived the equation that governs the rate of change of probability density function, and that turned out to be basically the classic diffusion equation, right? Which was very fascinating. Now, moving forward, we did the same thing in 2 dimensions. We said when we went from 1 to 2 dimensions, we could think of it in 2 ways. One possible way was, both the x component and the y component are randomly chosen, with both positive and negative values. The other way to think about this is, we can decompose instead of x and y, we can think of it in terms of the polar coordinates. So in polar coordinates, what you have is an angle and a distance you move, r and theta, right? So here I'm representing them as theta and d. For simplicity, we considered 2 distributions. One was that, the turn angle was, random, uniform between minus pi to pi, meaning, at every instant in time, it could turn in any direction. Okay, and the second one was how much do you move having turned randomly? That was also a random number. In the assignment, I asked you to consider 2 distributions. One was a power law distribution, other was a uniform distribution. Now remember that because now it's a jump length, this has to be a positive quantity. Okay, so in the context of uniform, we sort of considered from 0 to A. Okay, whereas in the context of just 1 second, I'll make sure. Pointer options pen. Okay. Yeah. So we had 0 to A, uniformly between 0 to A, and we have also considered a power law, which was from X min. And we also had a parameter, we had 2 parameter values. Now, when I asked you this question, I did not really define much about the power law. I hope you looked up the properties of power law. So power law has this, when you define a power law distribution with 2 parameters, X min and mu, you are not going from 0 to X min. So X min is the minimum value and the maximum value is actually infinity. Right, in the context of this one, the range of values were between 0 and A, whereas in the context of when I'm using PowerPoint, the eraser and all the options become a lot more complicated. Okay, this was in this range 0 to A, whereas this was in the range X min to infinity. Of course, there is a fundamental difference here. You start from some minimum value, go all the way to infinity, and I had asked you to choose X min is equal to 1. Okay, 1 to infinity. Very, very large distribution. Of course, in principle, we can consider any other distribution. Okay. Okay, so now we go forward now. So here is how, so I have taken the liberty to use the assignment submitted by Abhipsha. He has done a really, really good job. So I thought it's great for me to show you all the results. And of course, all of you also have done this. Okay, so this is how the trajectories of, random walks look like as you increase A. So A being 10 here, 100, 1,000, and 10,000. What do you think is changing, right? Obviously one thing is changing. Just look at the X and Y axis. Those values are changing, right? So you have a, much larger values of X and Y ranges as you increase A, right? Now it's, as you can see here, it's now gone to 15,000. Here it's actually 150,000. So these numbers are really increasing as you increase A. So 0 to 100 has now become basically really, really large, 150,000 or so, right? So the overall scale of the system is increasing. And of course here, remember that we are using a uniform distribution of jump lengths. But is there any other feature you notice? Is there any qualitatively as you go from 10 to 10,000? Do you see that? Is there anything else apart from the fact that you have a larger range that's happening?
I seem to see a lot of bunching in like larger values. Like there are a lot of these very densely spaced points together. I think
these ones, is it?
Yeah, that might be like just a consequence of that particular run, though I'm not sure.
Don't you think there's a lot of crowding here? Crowding here?
Yeah, there's not much in 10. That's the only basis.
I mean, it's, yeah, these are all single realizations. You could be right. We don't know. Yeah, it's possible, but okay, you think there might be some more bunching for larger values. Okay. Anything else that any of you notice? Okay, let's now move forward to looking at power law distributions again from Abhishek's assignment submission. Okay, so this is a power law exponent at 1.5, 2, 2.5, and 3. Do you see difference as a function of mu? I don't think I even need to say, it's very, very evident. Okay. So, but what is it though? So compare the axis ranges. right? So the range is, as you go towards mu is equal to 3, this range has become really tiny. Okay, so you can say that mu and A are inversely related to one another. Increasing mu is same as reducing A. Is that correct? If you were to map to uniform distribution. So that's about the scale and the range of values that it takes. What else?
So the incidence of like really high jumps decreases with increasing mu because of the this thing. So you can see more resolution because there are no really large jumps kind of dominating everything else.
Okay. Yeah. When you speak up, please tell me your name once. That would be really great.
Sure. This is Krishna.
Okay. Thank you, Krishna. So you can see that, across mu, there is clearly something that is changing. There is one long jump here, right? Huge jump here. Here you can see that the length of long jumps have reduced as you went from 1.5 to 2, right? And it has reduced further as we went to 2.5. It has reduced even further, okay, as we went to 3. So the long jump length that has reduced as you increase. What else happens? Let me tell something. In this one, it seems like there is a lot of movement happening here. It seems like they are stationary here. What's happening?
So in a power law distribution, you're more likely to get a small jump size because of this thing. And this is especially pronounced for increased mu because like you're starting with X min. So you get a lot of crowding because for a long period of time, you might get small values of jumps.
Okay, there's also a bit of an artifact here, by the way. This is just from 0 to minus 60 or 40, right? This is really 100 by 100 landscape, whereas this is, you can think of it 100 meters by 100 meters, whereas this is, 1 kilometer by 1 kilometer, right? Even more, right? So in that sense, it's entirely possible if I zoom into this part, it might still look like this. Okay, so what's happening here is overshadowed by this single long jump that you are seeing. It's possible that there is a lot of, movement happening in both of these clusters here, in one corner here and one corner here, exactly the way it's happening here. That's not very evident in this scale. Okay. Okay. Now, so basically you see two features here, right, in the power law distributions. One is there are long jumps, and then there are these clusters, local clusters. Let's call them local clusters and long jumps. Is that fine? Do you see such things in the uniform distribution? When you often see a long jump here, clearly there are clusters. But is there a long jump?
No, the clusters are connected by, I would say, roads of, like there are roads in between them where the roads are also created by small jumps, not large jumps. So there are a lot of small paths, like small walks that has
Maybe there is a small path here, as you're saying, some directed path here, but those are nowhere comparable to the long directed jumps you had in the power law, right? Okay. So there are these two striking they behave, the long jumps and local clusters. There are two features of power law that are not very evident. It's only, it seems like local clusters here in the uniform distribution, but there is no long jump. Okay. Now let me ask you a question. Now, if you think about this biologically, okay, now imagine an animal which is moving in this uniform distribution way as against, let's say, power law exponent 1.5 way. Now, what do you think are the advantages and disadvantages of choosing one type of random movement over another type?
So I feel that if you have like a power law distribution, it might be more useful when resources are scarce, because you can go to like take really large jumps to find new patches. Whereas if you have kind of abundant resources, uniform distributions might be better, because any length of step you take, you're likely to find something.
Okay, that's a good answer. But what if in the process of making a long jump, what if you miss a whole bunch of things in the middle? See, for example, in this case, right? This guy has taken a massive jump, right? Across the diagonal of the entire landscape, right? What if there were patches here, 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 here that was all missed? Don't you think there is a cost to all jumps? So I agree with the advantage part. You may end up with a totally new location, but also will you also not miss a whole lot of locations in the process?
So maybe you can modulate mu between jumps. Like maybe if you're modeling these as power law exponents and a patch might be exhausted, maybe the first few jumps will have very low mu in order to kind of survey the entire area surrounding. And if that all gets exhausted, maybe then the mu is modulated to a lower value so that.
Okay.
I think
Okay.
it's more suitable for seasonal migrations.
Oh, this one, 1.5.
Yeah.
Okay. But yeah, that's also a possibility. You really want to go for a long jump. But remember that for seasonal migrations, they're often to a very targeted location, right? But
Yeah, so there should be some memory.
Memory of where you went last year, right?
Yeah.
Or it must, whereas the current turning angle doesn't have memory, right? It just goes randomly at every time step.
Yeah.
Okay, cool. So you have taken on the right directions. Okay, let's now move forward. So what are the contrasting features? Again, I have taken the text as it is from Abhisha's homework. I think she wrote very well. So I'm just using it here. So commonalities, the range of values. When A is small in the uniform distribution, the range of X and Y coordinates is also small. When A is large, so is the range. The range and A are of similar orders of magnitude. Okay, that's the very interesting observation. And then if you think of power law jump length distributions, when the power law exponent is small, the range of the trajectory has very large orders of magnitude. The higher the value of the power law exponent, the smaller the range, right? So there's some commonality in A and mu. They seem to have an inverse relationship, okay, in terms of the range. Of course, there's an important contrast. In the uniform jump length, despite the change in A, the general appearance of the trajectories remains the same, with no distinctive differences apart from the fact that average distance traveled per time point increases with A. Although one of you seemed to say that maybe the clusters are more prominent with large A, that's not the observation of Bipsh, at least, which I actually agree with. And then how the important contrast comes from this cluster of points. The power law jump trajectories have several apparent clusters of location in the trajectory, while those of uniform distributions have no such well-defined clusters. There was an additional point we discussed, which is that of long jumps. So the long jumps that we see here are again absent in the uniform distribution. Okay. So now let's quantify this now, right? So it was a part of the homework, right? I think question 3C or so, where I asked you what is the MSD exponent as a function of A, and as you analytically expect, it's indeed exactly is equal to 1. In fact, it must be exactly is equal to 1. I don't know why it is slightly above here. It might be some artifact in my code. By the way, how many of you used my code I sent? Was there any mistakes in the way I was calculating anything? Was that okay? For calculating the mean square displacement exponent? Did any of you write your own code, by the way, or did you use was there anybody who wrote your own code? Just let me know. I can also look at that, how you wrote.
Yeah, I wrote my code.
Arshad.
Yeah.
Okay, thanks. I will take a look at that. Okay. So let me tell you something. I have used an extraordinarily crude statistical way to calculate mean square displacement of alpha. So whenever you have a power function, and when you fit data to power function, you have to be very careful. Okay, it's very easy to get the the estimates wrong for a bunch of reasons. Because often, whatever the nature of the curve might be, once you take double logarithmic, a lot of things begin to look like straight line, at least for a region of values. So because of which, taking the logarithm and then doing a simple regression to find out the exponents often gives you wrong estimates of alpha. I suspect that the reason why you see that there is every time it looks like MSD is slightly estimated as alpha is slightly above the expected one. I have a feeling it's probably because of that reason. Okay. In statistics, you may have heard of something called biased estimator and unbiased estimators. Okay. So I have a feeling that the simple regression based method is probably is a biased estimator, which means that the mean value of the estimator will not actually match with the input value. Okay. So usually whenever you're dealing with power loss, MLE, maximum likelihood methods, are much better. In fact, MLEs are better for most things. Something called mean maximum likelihood methods. So maximum likelihood estimators. So that's probably the reason why there will be some erroneous results you will find here, but that's okay. Since we're not doing a statistics class, this is totally fine. Okay. But nevertheless, this point will come up in the second half of the class today. But that technical part aside, this is something really striking, right? Whatever we exactly predicted analytically is now true. Of course, this is what you really expect. And indeed, that's the case. And what's really nice about what Abhiksha has done is she has not done for one trajectory. What she has done is she has done, she has effectively taken 100 trajectories of size 1,000 each. And then for each of them, she calculates alpha. And therefore, she not only has alpha, but also the standard error, if I'm right. Is that standard error or standard deviation, Abhiksha, that you're plotting there?
Standard deviation.
Okay, yeah. Standard deviation of the estimator. Okay. So this is in fact I have quickly gone through what many of you have gotten. I think most of you do seem to get this. Okay, except that it was a bit more noisy, and I think whenever you have gotten noisy, it's primarily because you have taken literally a single series. What Abhiksha has done is, she has taken a single series, but she has chopped them into 100 sub pieces. And then from each sub piece, calculate the alpha and then do an average of alpha. That's a very clever method, although technically you have one long series. Okay. Okay, that's as expected. Great. Now let's look at what happens to power law, right? So power law shows this really interesting feature that the mean square. So our analytically expected, right? Our analytically expected result is here. Right? 1. MSD alpha must be equal to 1. But where do you actually begin to find MSD is equal to 1, alpha is equal to 1? Only when alpha is greater than 3. Right? So what this means is something very interesting. We will actually find the features of Brownian motion, unbiased random walk, only when the power law exponent of the jump size distribution is more than 3. For values less than 3, you actually have a different value of, in fact, higher value of mean squared exponent. Okay, and this region is also called super diffusive motion. Whereas this will be diffusive motion. Okay, so this is where our analytical expectations have broken down entirely for power law exponent less than 1.5. Okay, I have again seen that many of you did get somewhat similar result. Is that right? Of course, if you haven't done the averaging well, you might get very stochastic patterns here. Any questions on this? Okay, so I'll move forward. So why does this happen? Let us try to understand what's so interesting and unique about power loss. So let's look at the graph on the left side here. On the left side, you are seeing two graphs. One is an exponential decay in orange color. Other is a power law decay in the blue color. So what you see here is that for exponential decay has higher density for low values, but it has much lower densities and has rapidly decayed with x for large values of the argument, right? On the other hand, power law decays relatively slowly. Now, this effect is very, very prominent if you do a log-log plot of the same function. Okay, so what you are seeing here is the orange curve is the exponential plot on a log-log axis, whereas blue is the power law with again log-log axis. Okay, so what you see very evidently here is that the power law decays linearly in log-log transformed axis, and the exponential has rapidly decayed. Okay, it is pretty much hitting zero, effectively zero very, very sharply. Okay, and this feature, the fact that these features of power law, these features are called fat-tailedness or heavy-tailedness. So power law distributions, and there are a class of distributions that belong to this. They are called heavy-tailed distributions or fat-tailed distributions. Another important distribution that sort of can be considered heavy-tailed or fat-tailed is log normal distributions. Okay, and what this basically means is that the large events, think of this as anything happening above 100 as large event. These large events are much more likely if we have a power law distribution than if we had an exponential distribution. Okay, so here we are showing exponential as a just to demonstrate, but you could have chosen normal distribution. Normal distribution decays even faster than exponential distribution or any other distribution. Okay, now what mathematically beyond visual differences of what is heavy-tailedness, we can also quantify and find some very interesting differences between power law and the exponential. If you think of exponential normal distribution, they all have a well-defined mean and a well-defined variance, right? However, if you think of power law, they have this very strange behavior. When the power law exponent is between 1 and 2, the mean value is actually infinitely large. Okay, and only for mean value greater than only when the exponent is more than 2, you actually have a finite mean value for the power law distribution. Okay, and now so basically now let's go back here. Beta and mu have been swapped by the way here. Okay, so let's go back here. So for these two values, basically 1.5 and 2, the mean jump length was basically infinitely large, which is why you are having this really incredibly large values of the x and y axis. It's not merely increasing to infinite. So that's sort of a crazy feature of power law. Are you able to hear me by the way? Because I got a message that the internet is unstable.
Yeah, able to hear you.
Thank you. Okay, so for these two cases, for mu between 1 and 2, the mean of the jump length is actually infinitely large. However, for 2 to 3, in the range 2 to 3, the mean is finite, but the variance continues to be infinitely large. Okay, and that's what this is telling. Okay, when for the range 1 to 3, not only mean, even though mean is finite now for more than 2, but in this entire range 1 to 3, the variance is actually infinitely large. Okay, which basically means the mean and the variance are not even well-defined quantities for a power law distribution. Therefore, if you now revisit our mean square displacement calculation, that now it begins to make sense. When you did that calculation, you made an implicit assumption that the mean and the variance were actually finite quantities. Therefore, all of those steps that you were doing were totally fine. Okay. However, the moment any of these to become infinite, our calculations that led to this derivation are not true anymore. Okay. So therefore, we actually have a different exponent for t here. Okay. And that explains this entire super diffusive region. The fact that So in this between 2 and 3, the variance of the jump length is infinite, but the mean is finite. And between 1 and 2, both mean and variance are infinitely large. And that explains this, the mean square displacement really going up, shooting up. Okay. So those are all the mathematical features of power law distributions. Any questions before I go forward? And that explains why you found the differences in the mean square displacement exponent. Any questions up to now? Okay, there are no questions. Let's go forward. So you can ask this question. Okay, now do these make sense for real organisms? So whatever you're saying, all the mathematical properties, do any of them make any sense to understand real organisms? Okay, that's what we will now focus on. Okay, so this is a very, very interesting paper on pondering Albert process. So these are shorebirds. Okay. Okay, so what they did in this study was that they had tagged 19 birds when they were going out on their foraging bouts. Okay, and the way this was in 1990s, early 1990s, right? They didn't have GPS collars and so on and so forth. What they had done was they had something called a salt logger. So these shorebirds, they sort of dive in the ocean and they forage, right? And then they die, and then they come up and then they fly again. So there will be regions. So in their salt loggers, we'll find that there are some occasions when the logger will notice that okay, now in this duration there is salt on the logger, but there is this whole duration when there is dry and there is no salt in that duration. Okay, so now let's not worry about how exactly salt loggers work. Think of it as something that measures dry and wet periods when the birds are foraging on the shore. Okay, and when they plot the locations of animals, this is how it looked like. Of course, this is from simulations, by the way. Okay, let me know, because they didn't have GPS tags to know where exactly the animals went. Okay, what they instead had was something different. What they did was the following. What they did was, because they had the salt loggers, they knew the wet and dry periods. So they assumed that the animals are moving at constant speed. So they looked at these durations of how much animal was moving. Okay, and what they basically found was that if you again look at mean square displacement from their data sets, I encourage you to read the paper to understand how they were doing all these things. Okay, they of course as we know, if you do root, so basically what they were calculating, root mean square displacement, which is really same as what we were doing, but it's square root. Okay, and they were expecting alpha is equal to half for Brownian motion, but what they found was the mean square displacement was actually 0.84. Now I'm sorry that you have to really switch from alpha that we were using was for the mean square displacement, but what they are calculating is for the root mean square displacement. I have made a mistake here. I should have written root. I should have called this symbol some other symbol. Okay, but I'm using whatever was there in the paper. So they estimated that these animals have a much higher mean square displacement than exponent than the random walk. Therefore, they are actually performing a super diffusive motion. Okay, and these are some plots that demonstrate what they had, what they're claiming. Okay, and so remember that they had not only by the way, the way they calculate this is actually slightly tricky. I would encourage you to read the paper. As I mentioned, they didn't really have the exact locations because they didn't really have GPS loggers, right? Like what we have today. So I would, they use a different method, and I'm not very sure if you know all the necessary mathematics to know how they get this. Okay, now what they also do is they look at the jump length distribution. How do they look at jump length distribution? It was based on the wet and dry periods on the salt loggers. If you assume that their movement had a constant speed, then the jump length will be proportional to the amount of dry period, right, in the forage. And what they did was they now look at the histogram of the this period, and what they find is that the jump length actually does not follow a normal or exponential distribution, but instead actually follows power law distribution, also called a Levy distribution, with an exponent mu is equal to 2. Okay. And what they then do is they run this, they consider Levy distribution model, okay, and with a random turning at each step, and they find that the mean square displacement exponent will be 1.8 in the way we have defined, because they are doing RMSD, right? We are doing MSD. It's actually equal to 1.6. Let me go back to Habib Shah's graph. So at at 2, they basically actually what the mission is about 2, mean square displacement about 2, but what they found was roughly around 1.6. Okay, these differences are reasonable because the statistical estimators are different. Okay, so basically what they said was the animals are moving, exhibiting these birds are exhibiting power law jump length distributions with exponent 2. That also explains the fact that the mean square displacement estimate they had was 0.8. Root mean square displacement estimate was 0.8. Okay. So they then explored what are the possible reasons for this. Why are these animals showing this behavior? In this paper, they arrive at some conjecture, which I think wasn't very satisfactory. What they claim is that most likely animals are following how the landscape is distributed. So they argue that most likely resources in the shore, they are fractally distributed, and if you track resources which are fractally distributed, you will also move in a fractal way, and therefore, animal could be exhibiting this power law. They also hypothesize that birds follow what are called thermals. Thermals are these, wind patterns which helps animal to float in the air for a very long time. They said that it's possible that the lifetime distribution of thermals could be a power law distributions. Animals are just following thermals; they're not actively flying; they are just following the wind motion. If the wind motion had this power law distribution of lifetimes, then the animals will also show the same amount of lifetime in the dry period in the flights. Okay, and they said that this aids another possibility they thought was maybe Levy flight could be a consequence of could actually be a solution for the search problem in complex environment. In this paper, they don't really elaborate much on this, but they only speculate 3 possible reasons. And then a few years later, they try to understand this Levy flights with more data and also more theory. What do? They first of all build a computational model where they assume that the target foraging sites are located randomly, and then the forager detects the target sites within some perception distance, let's call that RV, and then moves towards it. Okay, so basically they're animals are moving with a jump length given by a power law distribution. All these are also called Levy distributions with some mu, and they have these long flights, various flight lengths, right? In any of their flights and within the distance RV, if they find a resource, then they just turn towards it and consume the resource. Okay, and of course they also assume that the target site rejuvenates as soon as the forager leaves. What that means is that the resources are sort of they cannot be extinguished. They will just immediately rejuvenate as soon as the animal has consumed and left them. Another way to think about this, although resources are spread very patchily, but each patch has abundant amount of resources. Okay, so what they do is they actually show 2 results using some combination of analytical arguments and some approximations. What they basically show is exactly what we have been arguing all around. If there are abundant resources, the optimum value of power law exponent is mu. As we know now, a power law exponent of mu is same as the Brownian motion. Okay. On the other hand, when the resources are sparse, the optimum value of mu is 2. Optimum value of mu is 2. Okay. Remember that mu 2 is a very, very interesting point. At exactly 2, both mean and variance are infinitely large. But anything beyond 2, the variance of the distribution becomes finite, but the mean becomes finite, but the variance continues to be large. Okay. So this is what they mathematically prove. So let's say if you now go back to the these trajectories we saw long ago, here. So 1.5 to 2.5 and 3. This we know is Brownian motion. This we know has lots of long jumps, but I told you something, right? There's a trade-off. If you're doing this long jump, you may also miss a whole bunch of resources in this massive landscape. Okay. Whereas if you are doing entirely Brownian motion, it works well for abundant resource scenario because you're not really covering a whole lot of distance. So basically what they have shown is that this value of mu is equal to 2 is some sort of an optimum where you are locally foraging, but you're also making lots of long jumps. Okay, this is called global exploration. Long jumps help you explore global resources, whereas the short explorations also help you exploit local resources. To optimize local resources exploitation as well as finding unknown long-range resources, the optimum power law exponent is actually equal to mu. That's the mathematical or semi-analytical result from that paper in 1999. And then they show this in this result, the y-axis is some measure of foraging efficiency, x-axis is mu. As you can see, as you increase mu, the foraging efficiency increases. It reaches a maximum value at 2, and then it declines. Okay, you can again see the trajectories here. Mu is equal to 1.5. It's often a large path followed by a small amount of randomness. And mu is equal to 2 has these lots of jumps, but lots of local clusters. Mu is equal to 2.5. Doesn't really move forward. There is a lot of local exploration, and it becomes more and more so as you go towards mu is equal to 3. Okay, so it's basically, you can say, trade-off between exploration. Lower the value of mu will lead to more exploration, whereas values towards 3 will lead to more exploitation. So trade-off between these two will give you an optimum value of mu at 2. That was the main argument in this paper. Any questions up to now?
I had one small question.
Sure.
In our model, we're saying that essentially the organism will make a really long jump if there's no target it sees within a particular RV. So how feasible is it a strategy for an animal to respond to that by, instead of making a long jump, by increasing RV? Like, I don't know, fly higher so that you can see of an area or whatever.
But eventually there is some perceptual
feasible
limit for RV, right?
Right.
So what you need to assume is there is some perceptual limit for RV is some given. That's like given for an organism with some perceptual abilities, right? Okay. What you find is that independent of that RV, this pattern holds true. That's my understanding. Even if you vary that RV, this pattern of efficiency with mu doesn't change. Is that clear?
Yeah. Another small question I had, is it a random walk? Like, this is sort of unrelated, but is it a random walk if the position of things is sort of known in a landscape? So how basically linearly will an organism go from site to site to site to pick up food if it knows that where the food is or resources?
It doesn't know, right? It doesn't know. You see, this is a random walk, because one is jump length. What I have missed saying here in this as a list of assumption is they turn randomly. They are doing a random walk only when they see a resource within some perceptual distance RV. That's the only time they don't do a random walk. That's when they do a directed walk. And again, if you think of the entire landscape, right, The landscape had dimensions of the units of several thousand units per several thousand units, right? The scale was of that order, right? Even more depending on the value of mu. This RV is typically of the order of one unit.
Right. My question is, like, suppose the organism already knows where all the food in a particular landscape is.
Then this problem is there's no random search,
Yeah,
there's no search you have to do.
Will it just be linearly going from thing to thing, like?
Absolutely, yes. There are indeed animals which might be doing that. The animals with long memories, they probably follow such pattern. For example, think of elephants, right? Elephants have really good memory of the landscape. Not every elephant does, but the matriarch knows the landscape really well. In fact, they go to some very specific water holes in the specific times of the year. So yeah, absolutely, yes. So this entire theoretical framework is not applicable for those cases. For those cases when the animal knows the landscape really well. Any other questions?
So the plethora of stochastic optimization algorithms focus like specialization on various values of alpha and mu, right? Not alpha, mu.
Yeah.
So
in the power law distribution, yes, mu is the parameter to it. Yes.
Yeah. So for various functions, that they can like use different properties of the distribution.
So mu, power law is one function, but varying mu will just is you're changing one parameter in the function, and that's giving you different types of random walks. Super diffusive to diffusive. It doesn't give you subdiffusive motion.
Okay.
Subdiffusive motion, you have to change the model a bit. Yeah. Power law jump lengths won't give you, I think. Yeah. Okay. So this is what they found. This is the results of numerical simulations in 2D continuous space. Okay. So continuing on this. Okay. So now they also find evidence for this in empirical world. For example, they have data of, they claim that they have data of bees in high food environment, low food environment. When the high food environment, they show a distribution like this, whereas in low food environment, they show a jump length shows a distribution like this. So just visually, you can inspect that the low food environment does lead to these long jumps, which are absent in high food environment. And what they then did was look at the log transform data and they estimate the slopes of these. For high food, they found an exponent of 2.5, and they claim that for low food, they found an exponent of mu is equal to 2. Okay, of course, you can question how robust the results are, but that's what they claim in this paper. Okay, and then they also say the same thing with deer. Okay, they claim that they had data of deer, and again they find that the jump length distributions show a mu of 2. Okay, the exponent of 2. Now I'm showing you these two results. Okay, do you think there is something that you think might be a problem with this? With their conclusions? Just by looking at this graph, if you are the reviewer of this paper, what will you say?
Data points are few. There's only
Sorry?
very few data points.
Very, very few data points. What else?
The
Is there a data point that
sorry.
One by
if
one.
it is a straight line to a curve here.
We think it's not really a straight line. Okay, another
No.
point. Okay, fine. What else?
so they seem to be ignoring some points.
Like these points, no?
Yeah.
Okay, fine. But one can say this is justified because in power law there is this parameter called x min. I can always say that the power law is valid only after x min, whereas x min in this case is 7.5.
Okay.
Or what else? But the smaller number of data points is one issue. Maybe it is curved, maybe it's not a good fit. What else? Those are both are valid points. What else? If you are the reviewer, what else will you pick? Here also. Anybody? Look at the x-axis values.
Hello. Yeah, the range of values, like it's only from 2 to 3, and you would also expect there to be some points after 3, at least up to 5, I guess.
Yeah, may I know your name, please?
Sri.
Sri, exactly. Yeah. So what Sri is telling is the range over which they are fitting the data, right? Goes from, just think about this high food case. It goes from, well, let's be very liberal with them, 2 to 2.5, 2 to 2.6. So what is 10 power 2? 100, right? What is 10 power 2.6? Around 400, I think. Okay. What about this now? The low food area. So 100 to, if X was the meter, let us say you are fitting from 100 to 600. What about this? This is going all the way to maybe 1000. Let's be very liberal with them. And let's say again, very liberal, 2. Okay. 10 power 2 to 10 power 3, 1000. Now 100 to 1000. This is one full order of magnitude, right? Whereas this is half order of magnitude, not even full order of magnitude. Okay, so basically they are finding that there is a power law relationship in one order of magnitude at the best. Okay, now let's go back to the one figure I had shown you long ago. Okay, look at this. Okay, so this is like when you say one odd, basically when you are seeing a power law here, it's going all the way from 1 to 10 power 3. This is 3 orders of magnitude here, right? Okay, whereas one order of magnitude will be only from here to here. Half will be only from here to here. Okay, now let us say, let us say I go from in this figure, you can see more clearly between 10 and 100. Okay, so in this clearly a power law looks like a power law, right? 10 to 100. How about this orange line? If I were to focus only between 10 and 100, how does this look like? Can I not apply, if I had only this much data from here to here, will I not be happy to call this a power law too? Do you see my point? So what I'm trying to say is, if I were to fit, imagine if I had data only from 10 to 50. Okay, if I'm fitting only from here to here of an exponential, is it possible that I will think of it as a straight line? In fact, if we had any curve, if you take a small enough segment, it always looks like what? Any curve. If I take a small enough segment, it always looks like a straight line, right? Okay, so it always looks like a, it can always, especially if you now do a log-log transform and get stretched even more. Okay, so you are more likely to find a power law if you take a very small range of values. So one golden rule of thumb when anybody tries, if anybody ever tells you that they have found a power law, is check what is the range of values over which they are claiming it to be true. If it is not 2 orders of magnitude, don't trust them. Okay, so therefore, fast forward. Of course, at that time, nobody knew these statistical rules. Okay, everybody was happy with that, although they had only half order of magnitude where they found power law, everybody was very excited. Okay, so that, because of which there was a twist in the story. Okay, So what they did was, and there was another paper in 2007, what they did was they revisited this Levy flight search patterns. So basically they had new data now. They have high new resolution data of wandering albatrosses, and they find no evidence for Levy flight behavior. That's what this paper claimed. Surprisingly, in this paper too, Vishwanathan and others who were part of the original papers, they were also co-authors on this, which means they also agreed to it. And what they then did, okay, there was a very, very funny reason for this, okay. The reason for this was not statistical artifact alone, okay, something very, very funny, okay. That they actually find that a lot of long jumps were actually spurious. So you remember what I had told you in the salt loggers, the dry periods were taken as long, were taken as proxies for flight length, right? But it so happened that these birds occasionally came and sat on shores for very long times. Okay, so but this is something they did not know when they first did the study, in the previous decade. So basically, a lot of stationary faces of birds literally sitting on the shore, they were counted as long flights. Okay, so in fact, what they thought was a long flight was basically, somewhere they were in the ocean, the birds, they would fly, they'll come near on the shore, they will sit, and they go back, right? So basically, it was actually two short segments plus a lot of sitting time on the on the land. Okay, but this was counted as a long flight, and because of which lot of long flights that went into analysis were spurious. And I have anyway told you that their x-axis ranges were really not huge either, right? So put these two together with better statistical analysis, they basically found that it's not a power law anymore. It's not a power law distribution anymore. Okay, so this is the plot that explains along with all the statistics that says that better data and better statistical methods, along with removing those spurious things, if you account for those, you find that it's not a power law flight time anymore. It's not a power law jump length anymore. Okay, that's what they're saying here. Red lines are hours for which the logger was completely dry. Blue lines indicate the hours when the logger was wet for some part of the hour. Gray lines indicate switches between these regimes. Black lines indicate, okay, this, okay. Okay, all birds remained on Bird Island for long periods before departing, but such periods were considered to be flights in the original study. Intervals after these black lines were removed correspond, once they removed those sort of, spurious data, all the power loss apparently went away. Okay. Corrected data, they claim here, they don't show power law features anymore. So this was the original data. Okay, this is the data after correction, and you can see it is now really bending. Those large flights are now totally removed. Okay, so here is one food for thought for all of you. All of you have heard about retractions in scientific literature, right? Have you all heard of retractions?
Yes, yeah.
So what does retraction mean? Why? When do people retract papers?
When there have been certain issues with the method or methodology, or if the results are spurious, like in this case.
Right, like in this case. So basically, you are concluding that in this case, there were probably enough grounds to retract the original paper where they claim that albatrosses exhibited power law. Is that right? So it's worth thinking, when should one retract papers? And do you think this merits a case, for retracting the papers? Because basically they did some analysis, they found some really cool results, but 10 years later, they found that one assumption that went into the analysis was totally wrong. And if you now correct for that assumption in the data, the original conclusions were not right anymore. Okay, which means that the original paper was wrong. Does it mean the paper must be retracted? You should go and search in the literature whether this paper was retracted. Okay, so it's something that everybody must think through. It's actually a very interesting question, especially in the context of this paper. Okay, any other thoughts from anybody else? if whether a paper that has been found wrong should be retracted?
I think they should just add a corrigendum to the original paper, not fully retracted.
Why not? It's been now proven now. It means we have, they themselves are admitting, right? It's not even a contest between two groups of researchers.
Yeah, but retraction, I would assume, for when you discover deliberate malpractice or something like that. Data
I think retraction
forging.
must be limited to malpractice alone.
Yeah, that is my view.
Okay, that's one viewpoint. Okay, yeah, and you also what about others? Anybody else? So one viewpoint is that retraction must happen only when there's a deliberate malpractice. What's a non-deliberate malpractice?
I think like
Malpractice is by definition deliberate, almost deliberate. No. Yeah,
no,
go ahead.
about the
Yes.
retraction. About the retraction, I think like the literature should also have like failed attempts.
Mm-hmm.
Like how some attempts
Okay.
were not really successful, and like they should link back to the correct one, but still like the wrong results also should be there, like to show that like things can go wrong also.
Okay,
I
that's
think
another
I
very
agree.
interesting.
I agree with the person who spoke just before me, but I think in this case, they made an outright mistake.
Okay.
So in curating their data, if they had found something and they whatever hypothesized or inferred a particular conclusion from their data, and that turned out to be wrong, not their data itself, then I think it's not grounds for retraction. But in this case, I think the data itself is erroneous, and so should be.
Okay. The data itself is never erroneous per se. No, data. It's hard to distinguish data and the interpretation of data itself. No, because they truly thought it was data, but what you now know is it's the data itself had a problem, right?
They used the data that was good at the time. Like the short
When they use
logger
the data,
had its flaw. The method has had its flaws, but like it was found out later only.
Okay. So one viewpoint is that since it has been found wrong, the conclusions have been overturned. Therefore, the previous one must be retracted. The other viewpoint is that there must be room for recording the mistakes, right? Therefore, a corrigendum should suffice, right? A third viewpoint is that in this case, the data itself was erroneous. Therefore, in this case, it's not a question of one specific conclusion being wrong. The data as well as the conclusion, therefore, are both wrong. Therefore, it must be retracted. Okay. What else? Any other viewpoints?
I mean, this isn't a viewpoint, but a question rather. So if the authors of this paper themselves have, along with other people, have published another paper which explained the reason behind their erroneous data, then what does retracting this paper achieve? Like, because any further research that is carried out from the paper will of course take into consideration this original paper plus the additional one that came later, right? So retracting this one makes no difference.
Okay. Anyway, I think by the time this 2007 paper, I think this paper probably had several hundreds of citations, and there were whole branches of subfields within physics and mathematics, and as well as biology that had developed. I think even now, if you go and look up, this paper probably has 1,000 citations above. I don't know the exact number, but you should look up. So it was a very influential paper whose conclusions are probably wrong.
Yeah, so in that case,
as of 2017. So yeah, go ahead. Yeah.
So if the question is whether you should retract it now, then I don't think so, right? Because now we have the result, but it should have been a question that should have been asked way back then.
Okay, so let me ask a following question, right? So if a research has led to a lot of thinking in the field, lot of subsequent papers, a lot of subsequent ideas, but the very original paper was turned out to be wrong, if you now suddenly remove the paper from the record, right? Isn't it like, removing sort of, foundation stone? All the foundation stone was faulty. It is stuck now. It's not a case of, foundation stone falling apart, but it actually has led to a lot of new things, right? So the, original idea that led to a lot of further ideas will just, in other words, people will not know what was that paper that led to so many other papers. So there'll be 1,000 papers citing one paper X, but if you now, go to the journal paper, that paper will not be accessible to people anymore. Is that really desirable? Okay, this is an important point to think. Another point to think is, if you take papers from 1900 to whatever, it's a 1950, okay, especially new areas of research at that time, or any 25-year window where there is a new area emerging. And then if you look at the end of the maturation period, how many of the ideas that were initially really proposed and found to be true, how many would still hold true? Don't you think most of research probably in the initial stages of a field will be wrong anyway? And they get superseded by the collective knowledge of the people over time? Or if you want to truly retract, you have to go back and retract all the papers from all the centuries, all the papers were wrong. Why only one paper?
I think if you retract like all the foundation papers that first came, we kind of erase how we learned the field.
Exactly.
How
that's
people
exactly.
started learning that field.
Yeah.
So
that's
then,
also a very important point.
Like it's kind of neglecting how we learn.
Or sort of, erasing history.
Yeah.
Right. Yeah. Historical development. We have erased the historical development, right? Yeah. So this is a useful. So retraction must be viewed in this broader sense, right? And therefore must be very limited. And one can think, where to draw the line. It's not very obvious actually. Okay. Anyway, I thought this is an interesting point to raise in the middle. Okay. Now let's fast forward in time. I think I'm almost coming to an end. Okay. But there was a more recent paper. This was a paper in 2012, I think. They find something very interesting, which is that, I'll just read the, okay. Do you have the entire thing? No. Okay. Okay. So I won't go through all the details, but interestingly, what this paper now says is the following. These results, together with our reanalysis of previously published albatross data. So these results had lots of marine organisms. Okay. I think they had two types of albatrosses, not only one albatross, wandering albatross and black brown albatross. Okay. And this person, Humphreys, they have also, Humphreys, have also done, I think, the analysis with many marine organisms as well. Okay. What they find is that what they basically claim is they overturn the notion that albatrosses do not exhibit Levy patterns during foraging. The main point of this paper is that the new data that they used, and they reanalyzed the previous data that Edwards et al. Had reanalyzed the previous data. Okay. And they basically conclude that, they themselves had made some there were methodological issues. And if account for all of those along with new data, they again find evidence for Levy flights. Okay. So imagine the original paper was now retracted. Right? Okay. That's useful to think, but I'm not going to details of all these papers, but the reference now, and if any of you find this interesting, you should dig up all these papers and how actually all this sort of happened, and that sort of introduces you how the messy world of real science, where you sort of go back and forth between some various evidences and the inferences we come about. Okay, so that's the end of the class today. So I haven't gone into the details of all the papers, but I encourage you to upload the papers. And these papers may also give you some ideas for the project that you have to do in the course. Okay. Okay. So any questions? Okay. So there are no questions. I will stop here. Okay. So we will meet on Friday again. So now about the homework, what I will do is, I will prepare, I'm going to largely use, I have taken Abhipsha's consent. She has very kindly agreed that I can use her solutions. So I'm going to largely use her solutions as a model solution, and I will upload it. And what you will all do is something called peer review. So you will be randomly assigned somebody's homework to review. Okay. Using the grading scheme that I will, send you within a day or two. Please grade whoever is assigned for you to grade the homework. Okay. And in the process, hopefully, you will also learn to grade. And I will send you a bunch of instructions how to grade. The purpose of grading is not to cut the marks, but to be constructively critical. Okay. Okay. So, and it will also be good for you to learn how to read somebody else's writing. And, you will also realize as a process that how we, when somebody else writes, and when you read that, that is, that's when you will begin to realize that, oh, my own writing was not very clear when I was writing, my homework submission. Okay. So I think there'll be a lot of interesting thing to learn when you actually peer review your own, group's homework. But I will send you a grading scheme along with the Pipsha's, solutions. Okay. So I will do it hopefully in a day. And then by this weekend, if you can, that will be really great. Okay. So we'll meet on Friday again. If you have any questions, you can have some time to answer. But otherwise, you can leave now. Thank you.